So,
So, hi everyone. Thanks a lot for coming today at PSC Learn and Share session. We are delighted to have Binyi Chen presenting LatticeFold and its application to SNARKs, sorry, six-sense proof system. Binyi has been working on quite a few different projects, OBUS RAM, memory card memory, and of course, lattices and SNARKs with LatticeFolds today. So thanks a lot, Binyi, for being here and for today's presentation.
yeah, thanks, Raphael. Thanks for introduction. And yeah, it's a really pleasure to be here. And I think it's for the third time. And today I'll present LatticeFold, which is a new scheme that allows you to build a succinct proof system for really large statements. So it is plausibly post-quantum secure, but even more surprisingly, hopefully after this talk, I can convince you that it's actually very, very practical and efficient. So let me start with some background on SNARKs. Suppose there's a verifile like Alice. She has a very, very old iPhone, but she wants to perform some computational expensive tasks, which also involve some large secret witness that she doesn't have access to. For example, she may want to ask a ChatGPT some question about her local information, but she doesn't have the large language model that OpenAI have. So in this case, what he can do is to send this question to some powerful party. And so I saw the question in the chat. Plausibly, is that we are always on some assumption, right? So that's why. But you can trust me that I think is post-quantum secure. Okay. So and let me continue. So in this case, he sent this question, and then the powerful party will be responsible for computing this function using her large secret witness and send it back the answer. But here the question arises, okay? So the verifier, how does he know that this is exactly the correct answer instead of some junk information, right? And one way to achieve this is to ask the powerful party to attach some small proofs called succinct non-argument of knowledge proof, so that correct verification of this proof implies that the powerful party indeed knows the large secret witness and this computation was done correctly. And a key requirement for this proof is that it should be very, very short so that it's easy to send to the verifier. And moreover, it should be very cheap to verify, even if the verifier only has a very, very old iPhone, okay? This is just a toy example, but in practice, there are tons of applications for SNARK proofs in scaling blockchain and machine learning and fighting disinformation for photos and videos and etc. And in the recent year, there's a higher demand for having a prover-friendly SNARKs, meaning that even if you want to prove some very, very large statements and very, very complex statements, you should be able to generate this proof relatively efficiently. So to do this in the practice, in the real world, I would categorize that there are two classes of SNARKs. Well, I would call these traditional SNARKs as monolithic SNARKs, which generates this SNARK proof all at once. And in the literature, there are many such schemes like Gross16, Plonk, Hyperplonk, Spartan, Bulletproof, etc. And even in the post-quantum setting, you have some really nice candidates of proof systems like STARK and etc. And in the post-quantum setting, usually they have relatively larger proof sizes. And also for those practical lattice-based proof systems, they usually have a very expensive verifier, which is usually has linear time complexity. But in general, for many of the schemes, they are working pretty well for those mid-level sized statements like arithmetic circuits for 2 to the 16 gates. However, when it comes to prove some very, very large statements, like an arithmetic circuits for 2 to the 30 gates, they have some caveats and there are some limitations there. And one of the key limitations here is that you have to fix these statements and also get the witness, even if you before you start doing the proving. So to illustrate, let's consider example. Well, suppose you want to prove the correctness of a block of 10,000 Ethereum transactions are executed correctly with respect to some updated ledger state. And then as a prover, you really have to gather all these 10,000 transaction information and re-execute them and transform this execution transcript into some very, very long vector of extended witness. And only after that, you can start doing the proving. But at that moment, you already waste a lot of time, right? And moreover, because this witness is really, really large, you have to use some really large like memory machine in order to fit this input into the SNARK machine and run the SNARK algorithm. And also, it's very hard to get a very nice parallelization unless the SNARK scheme itself is parallelization friendly. So given this, an alternative strategy is to construct a piecemeal SNARK that is based on this incremental verifiable computation or proof carrying data. So the high-level idea is the following. Say you have some very large complex statements. The first step is to split these large statements into many chunks of small statements, where each statement is for some uniform smaller relation. I will call it R chunk here. And in generally, we note that there do exist some recent work called Mangrove that tells you that we do have some very efficient transformation from some arbitrary arithmetic circuits to a bunch of uniform statements. So this step is actually pretty cheap and efficient to achieve and to instantiate. And after having this many chunk of statements, our goal is to prove the correctness of all these chunk statements using some recursive strategy to obtain a small SNARK. So specifically, let's say we have already split this large statement into many chunk of statements, this shaded rectangle here. And then one way to do this is that we can build a binary tree, for example, and assign each node of the tree a chunk statement. And moreover, for each node of the tree, we'll generate some SNARK proof for the following statements. So first, we'll prove that indeed this local chunk of computation statement is correct. And second, we'll also prove there exist two SNARK proofs, which are the SNARK proof generated by the two children of these nodes, and they are correctly verified. And here, the essential requirement here is that this proof should be very, very easy to verify, should have some sublinear complexity with respect to the statement size. And this is essential to avoid the circuit size blow up when you do the recursion. And finally, when you obtain the SNARK proof for the root nodes, and this proof can serve as the SNARK proof for the original really, really large statements. Why? Because this proof implies that this chunk statement at the root is satisfied, and by the recursive arguments, because the two children proof are also verified, that means the chunk statement in the left subtree and the chunk statements in the right subtree are all correctly verified and satisfied. And that means all the statements in this tree are satisfied, and that implies the original large statement is correct. So this is the high-level strategy, and it's obvious that it has the advantage that the memory overhead is much smaller and is very, very streaming friendly. And this memory size is only proportional to the statement size of this R chunk rather than the original really large complicated relation RC. And also it enables some very generic strategy for parallelization where you can do this compute this tree along with each branch of the tree. So it's very parallelization friendly as well. However, in practice, until very recently, there's no one using such a strategy. Why? Because they introduce some noticeable extra recursion overhead. First, for each node of the tree, you have to generate a separate SNARK proof. And even worse, in this SNARK proof, you have to prove something beyond this local chunk of statements, right? You have to verify that these two SNARK proofs are correctly verified. And the SNARK verification circuit is actually sometimes very expensive to represent it in an arithmetic circuit. So that's why it is actually not that practical if you directly do this. So to address this limitation, recently there are many works trying to come up with and build a new scheme or new primitive called folding scheme to reduce the recursion overhead. So at a high level, this scheme works as follows. So say we have some relation. Well, the instance is some short commitments to some witness, and this witness also satisfies some other predicates. And then suppose we have two instances with the pair, C1W1 and C2W2. Then this folding prover algorithm will do some computation and output a folded commitments and witness, and also some small proofs. And later, the folding verifier, after getting these two input short commitments and this one output commitments and this proof, will check that indeed this output commitment is consistent with these two input commitments. And by consistency, usually will just mean that it's some correct linear combination between C1 and C2. And one important property here is that this knowledge sums property, Well, even for some possibly malicious prover algorithm, if she can come up with some output commitments and the proof such that it passed the verification, and moreover, if she knows some correct witness for these folded commitments that is in the relation, that implies there exists some extractor algorithm that given black box access to this malicious prover can actually know and extract some witness W1 and W2 for the original input commitment for C1 and C2. So in some sense, it's kind of a reduction algorithm that's reduced the checking of two statements into one statement. Okay, so with this scheme in hand, let's see how we can construct a more efficient piecemeal SNARK. For simplicity, let's just assume that there do exist a transformation that splits the large statement into many chunks. And for now, let's just consider a chain instead of a tree, but as ideas are similar. And now, suppose we have folding scheme, let's see how we can build a piecemeal SNARK. So to do this, we'll come up with the default commitment openings first, which may be some commitment to a zero vector. And then we'll continuously apply this folding prover algorithm to merge these online statements, C1, C2 to Cn, onto to update it and merge it into the new folded commitments and openings. For example, in the first step, I merge C1, W1, and CFD0, WFD0 to obtain the new commitment openings, which is CFD1 and WFD1. And in the second step, I'll do something similar and obtain the next folded commitment openings. And then do this again and again for n times. And finally, I will obtain the final merged single statements here, CFDN and WFDN, which is the accumulation or the folding of all these online statements that we want to prove correctness for. And at this step, after doing this, it seems that the verifier only needs to check the correctness of these final statements that is in this small relation R chunk. And the correctness of this implies that all these previous chunks are correct, right? However, I haven't talked about something about the authenticity of this output commit CFDN, right? So actually, I also need to make sure that this prover is giving you correct folded commitments that's consistent with this C1 and Cn. So basically, you want to prove that in each step, I do the folding correctly. And one naive way to achieve this is to ask the prover to also send these corresponding commitments C1 to Cn, and also the folding proofs. And the verifier will check for each step this to call this folding verifier to check that in each step the folded commitments are computed correctly from the previous commitments and the online statement CI. But this is not efficient, right? Because the communication is linear to the number of chunks, and the verification is also linear to the number of chunks, where you have to call this folding verifier for n times. So that is not enough for constructing a real SNARK. But fortunately, the correct solution is actually not much harder. Well,
I'm sorry. Can I ask something?
Sure,
so,
no problem.
Actually, you can make of square root of n chunks, right? And then it will give you a SNARK with square root of n verifier, because you will spend square root of n time to check the foldings, and then, provided your chunk verifier is linear, it will also take square root of n, of square root of n, right?
I see.
And this is actually something which is done in breakdown. So breakdown can be looked upon as a sort of very rudimentary folding scheme, which only folds like I mean, this is also doable.
I agree. Yeah, that's good point. Good point. So I agree that gives you square root n, but it cannot. I think it cannot do anything better using this strategy, right? Because in the last case, you do square root n, and in the middle, when you check, you also need to do square root n. And I think our goal is to have like logarithmic or even constant.
Well, at some point you will hit recursion threshold, but it will be quite large. So ideally you want better.
Yeah. I want better, definitely. Yes. But that's a good question. I agree. That if you can make n to be square root of the statement size, then even using this naive strategy, you can get some square root and solution. But I want to do better, okay? So So the way to do better is that you can embed this folding verification inside the relation you want to fold. So basically, the only difference here is that the relation you want to fold will be slightly more complicated, will be expanded relation, then also embed this folding verification. Okay, and then the relation we want to fold is now proving three things. So first, the witness is a commitment, is an opening to this commitment. And second, as before, we want to prove that this local chunk of statement is correct. And finally, that this folding verification was done correctly at each step. So because it's already embedding this relation, we don't need to apply this folding verification by the final verifier anymore. And here, the key advantage of a recursive SNARK are twofold. So first is that we replace the SNARK verification in the relation with a folding verifier. And this folding verifier is actually much, much simpler than SNARK verifier. Usually just checking a single linear combination of two commitments is consistent with output commitment. And second, even better, we don't even need to generate a SNARK proof at each step. We don't need to generate any proof in each step for prover. What he needs to do is just to come up with the instance with this pair for this relation and do folding. Okay, so because of this reason, it gives a much, much more efficient piecemeal SNARK compared to a recursive SNARK solution. And now the question reduced to how can we construct a very, very efficient folding scheme. So in the literature, usually the relation we want to fold follows this kind of format, where the instance is some short commitments to the long witness that is further nearly homomorphic. That means that it's very easy for you to do the commitment folding by doing some linear combinations. And in all previous schemes, they are using Patterson commitments, which is not surprising, right? Because it's a linear homomorphic, it's pairing free, and it has no trusted setup, which are all good features. However, they still have some caveats here. So in terms of security, they are based on this discrete log assumption, which is vulnerable to some quantum attack. And in terms of efficiency, they still have some caveats. First, in order to build an efficient piecemeal SNARK, they need to use this so-called pair of cycle curves that's a more complicated implement and also slightly less efficient than some regular elliptic curves. And moreover, for representing this circuit for folding verifier, even though it's much simpler than SNARK verifier, it still has some like overhead there. And the reason is the following. Because in this folding verifier, it usually involves two types of computation. The first is this elliptic curve scalar multiplication or group exponentiations, which is done over the base field of elliptic curve. And beyond that, there are also some other field operations that it would be done over the scalar field of elliptic curve, like those hash operations or some other field or arithmetics. So that means you have to do two types of computation over two different fields. But unfortunately, an arithmetic circuit can only be over a single field. So unavoidably, you have to simulate some field operations in a different field, which is actually pretty expensive. And that's also one of the main reasons that this recursive circuits for folding is actually not super efficient. It's still efficient, but still has some overhead. And on the other hand, we see that there exists no lattice-based folding scheme in the literature. And I want to mention that it's also it's not straightforward to extend those lattice-based proof system to a folding scheme, because all those practical lattice-based system has linear time verifier. But we already emphasized before that we really need this embedded folding verifier or SNARK verifier to have sublinear complexity in order to avoid this circuit blow up size. So that's not trivial. Hence, we ask this natural question, can we construct a post-quantum secure and concretely efficient folding schemes? So first, we want post-quantum security, and second, we also want it to be concretely very efficient. And the hope is without we don't need to dive into this recursive SNARK route where we have to verify some STARK or SNARK in the recursive circuits and generate recursive proofs. So here's our main contribution. The first contribution is that we introduced LatticeFold, which is the first lattice-based folding scheme that's based on some rather standard lattice assumption called the module shortest integer solution assumption. And even more surprisingly, we actually achieve very competitive efficiency versus those top free quantum folding schemes. And along the way, we also introduce some many folding techniques for lattice-based commitments, which might be of independent interest. So now, for now, any questions? I saw there's many chats in the chat, but I cannot see this. Rafael, you want to mention any of the question?
It's not really questions, it's more remarks on research. So Lev was talking about the fact that there is a homomorphic folding. It's really
I see.
about weak salt.
Yeah, I will talk about that in the end of the talk. So
perfect.
yeah, cool. Okay, so let me get started to the technical meat now. And for easy illustration, I'll consider a simpler problem here, where I just need to fold this commitment opening relation rather than the relation I mentioned before. But that already covers most of high-level ideas. So let me quickly recall some background. So recall that in this relation to be folded, usually the instance is some short commitment that's linearly homomorphic. And now, since we are now in the lattice world, the first scheme come to mind is this anti-compact commitments or anti-hash functions introduced by Atai in 1996. And I want to highlight here that this is actually very, very efficient. So with appropriate implementation and optimization, you can actually approach the performance of some widely used hash function like Poseidon hash function. So it's like, I would call it the almost symmetric crypto. So how does it work? So let's say we are working over some ring, like integer is a ring, but now we'll consider some polynomial ring, like a ring of integer for this second atomical field. And you can understand it as just some polynomial with integer coefficients. And each element will be a ring element. And now suppose we have a message vector W, which is of length n, where and moreover, we have to constrain that for each element in this vector, they have a rather small norms, meaning that the integer coefficient shouldn't be too large. And for this message, to commit it, we just multiply it by some public random matrix A here that has very, very narrow, like very few number of rows, that's n columns. And this will give us a very short commitment C that is independent on the length of n. And as a commitment, it had to satisfy this binding property, right? So that means it should be hard to find two messages in the message space that leads to the same commitments. And this is true for Atai under some standard lattice assumption called Module SIS assumption. Intuitively, it means that given some public random matrix, it should be hard to find a small norm vector x such that ax equals 0. And to see why this leads to the binding property is that suppose for contradiction, you have two small messages, W1, W2, that gives you the same commitment C. Then if you subtract them together, W1 minus W2 is another small norm message that is a solution to Module SIS, right? So then you can break the Module SIS assumption. So that gives us the binding property of these Atai commitments. And beyond that, you also satisfy really nice linearly homomorphic property for small norm messages. That means given the addition, like the addition of two commitments can also be understood as the commitments to the addition of the corresponding openings, so long as these openings are small norm messages. This follows directly from the linear homomorphic property of matrix multiplication. Okay, so that's some background about Atai commitments. And we will use these commitments in our folding operations. And now the question is, how can we fold this kind of commitment opening relation? So I would
can I ask a quick question?
Mm-hmm.
So as far as I understood, the commitments are for integer vectors, right? So they're not over.
Commitment is not integer vectors. Can I go back? Wait. Yeah. So the message is some integer or like some ring elements that has integer coefficients that has small norms. And this matrix A is over RQ. You modular some prime modulus Q here. And this
so they're actually also over RQ,
yeah,
but
C
small,
is over,
but small.
Yeah.
And Q is larger than this norm bound.
Yeah, C has A and C both have no norm bound. We only have norm bound for W, which is some ring elements, polynomial elements with integer coefficients. So this integer should be very, very small. and every A and every C are over RQ. And Q is some modulus that has no norm constraints. It can be over arbitrary RQ elements.
But it must be larger than your norm bound.
Yes, can be larger, can possibly be larger. Yeah, definitely be larger. Q is larger than this norm bound. Yes, exactly. Okay. Does this answer your question?
Yes.
Okay, thank you. Cool. So now, so the commitment opening relation we want to prove is the following. So given a tuple, a commitment C and an opening W, we want to, it is in this relation if C equals A times W modular Q, and also the norm of this W vector is small. And here we use this infinite norm, which means it's the maximal of the coefficients of every element here. And it should be smaller than this parameter capital B here, which is also smaller than this modulus Q. And some B is some parameter bound that we can choose. So now given two commitment openings in this relation, the naive way to merge them into a single statement is just to use random linear combination, right? Which is exactly the high-level idea of all the previous pre-content folding schemes. So now what we do is just we use this random scalar in RQ to merge these two openings into one, and hopefully that it will still be in the relation. However, the key point here is that in the lattice world, this can become problematic, and this folded opening might not be in the relation anymore. The main reason is that after this folding, the norm of this message can be much larger. And this can hold even if this random scalar is small. For example, even if you just do an addition, the norm of this WFD can now becomes 2B because W1 and W2 can be as large as B here. And then because it's larger than B, it's no longer this R type B relation. And you may wonder, why can't we just adjust this parameter B here after each folding step? So after each folding step, I will set a larger B for this relation. But this is not desirable in the folding scenario because that means after several folding steps, this norm bound will blow up really quickly. And at some point, we exceed some threshold. And after exceeding this threshold, this commitment will no longer be binding and secure. So that's not good enough. And therefore,
so I'm sorry. I also this is also a thing that I do not exactly understand. If, for example, like I know that in your paper you actually use quite small Q in practice, but imagine your Q is, I don't know, a few hundred bits, and this R is 128 bits or something like this. Then if you are doing linear folding, not tree-like, but along a chain of foldings, then you can fold in quite a lot of moderately vectors with some moderate bound, because the things that are folded in are always 128 bits plus norm of the non-relaxed instance, right?
That's not that simple, because first B here usually is much smaller than Q in order to obtain the security level. Like Module SIS assumption requires this B to be really small. Usually it should be much smaller than Q.
So my question is, can it be larger than 128 bits? Significantly larger than 128 bits, which is required for R.
You mean B, or you mean
the norm bound, the norm bound at which your commitments are.
The norm bound usually can be much smaller than Q. And say, for example, if you choose R to be some 128-bit scalar, then it's very easy for you to fold, and then the bound will be as large as 128-bit scalar, right? And and usually it's very insecure. Like basically in that case, is like, for example, you use 256-bit modulus Q. You sometimes usually really need some B to be as small as 2 to the 32 or 2 to the 64. And that means after like very few number of folding steps, it can blow up and exceed this threshold. And this module SIS assumption will no longer help you to obtain the binding property. And actually, there are some other also some other subtlety. So usually, I believe that if you you relax this restriction, it would be very hard for you to obtain a secure scheme in the folding scenario. So I think the best thing you can do is to really need to make B as small as possible, and not as small. You really need to be fixed, and then this enables you to do folding for infinite number of times rather than just very few number of times. Yeah, which is very important. Okay, yeah, but thanks for the question. It's a really nice question. So now to address this limitation and obtain a folded witness that is still in this relation, our first idea is to massage this input opening a little bit. Okay, so how to do that? And the idea is to in order to merge two statements into one statement, our idea is to do it in two sequential steps, where the first step will split a vector of norm B into multiple vectors that have even smaller norms, like this small b that's even smaller than b here. And the hope is that after this decomposition, then we can do the folding. And as long as we are using very small scalar, and after the folding, the folded statements now will have some opening that's still smaller than this capital B. So we can still obtain the same statement in the same relation. So that's a high-level idea. But however, to argue it more formally and clearly, let me digress a little bit to introduce this notion of reduction of knowledge, which is introduced by Kosapani and Brian Parnell in 2023. So the idea is the following. Suppose the initial goal is to check some statements in some complicated relation R1. And to do this, we'll run some intermediate protocol pi that after running this pi, it suffices to check some other statements in some simpler relation R2. And this is why it's so-called reduction of knowledge from R1 to R2. More precisely, say we have some public commitment C1, and the prover also additionally has some witness W1 for C1 in the relation R1. And then we run this protocol. And after this protocol, if verifier accepts, we output some update commitments. And if prover is honest and knows the witness W1, they should also be able to obtain a corresponding witness W2 such that C2 W2 is in the relation R2. And this is what the requirement called completeness requirements. And the interesting property here is that it also needs to satisfy this knowledge soundness, meaning that suppose for a possibly malicious prover, if she can obtain a witness W2 for the update commitment C2, then that means he also knows the corresponding witness W1 for the input commitment C1 that's in the relation R1. Okay, so that's why it's called reduction of knowledge. And there are many special cases for this notion, including arguments of knowledge and folding schemes. For example, folding schemes can be understood as that the R1 is just the product of two relation R here, and R2 is just a single relation R. And the goal is to reduce the checking of two statements in R into one statement in R. And the nice property here is that this notion allows very easy composition. For example, suppose you have protocol that reduce R1 to R2, and the protocol that reduces R2 to R3. Then if you compose them together, okay, then you can obtain a reduction of knowledge protocol from R1 to R3, and which seems very natural. But this paper has formally proved that this is the case, and this is very useful in our setting. And now let me rephrase our high-level idea in the language of reduction knowledge. So now remember that our end goal is to reduce the checking of two statements in this relation into one statement in this relation. And we achieve this by constructing two reduction of knowledge protocol and compose them together to obtain what we want. Okay, so the first protocol is this so-called decomposed protocol that reduces the statements, checking of the two statements in R type B to the checking of multiple more statements in R type small b. And then after that, I'll construct another folding protocol, which is another reduction of knowledge that reduces the checking of these many statements into the checking of these single statements in R type capital B. And the composition is exactly what we want. So now it reduced to question of how can we instantiate this decomposed protocol and folding protocol efficiently. So let's start with this decomposition. And And for simplicity, let's just see how to split a single vector into two vectors with smaller norms. But idea can easily generalize. So recall that in this opening of Ri type capital B, we have some input vectors, openings, which is a vector of ring elements, where each ring element is just a polynomial with integer coefficient that's in the range between minus capital B and B, okay? And the way to split it into two vectors is the following. Well, for each single integer coefficient of single ring elements, we'll represent these integer coefficients using these base decomposition representations. For example, if B equals 2, this is basically just a binary representation or bit decomposition of an integer. And we'll do this decomposition for every integer coefficient of the vector. To illustrate, let's consider a very tall example. We'll say this vector is only of length 1, and there's one single polynomial, 7x plus 8, which have relatively large coefficients that's less than 9. I want to split into two polynomials that have even smaller coefficients, that's smaller than small base 3. And then we can easily do this decomposition and split into two small polynomials, 1x plus 2 and 2x plus 2. And the nice thing about this splitting is that if you multiply a matrix A on both sides, this equality will still hold. That means the other commitment, the corresponding other commitments also satisfy this linear combination relation. So this leads to a very natural way to do the decompose protocol, where the honest prover, if she has a correct witness F, then he can do this splitting algorithm and split into two even smaller norm vector F1, F2, and then you compute the corresponding item commitments, and the verify before outputting the updated commitment C1 and C2, we'll do a one last sanity check, checking that C1 and C2 is consistent with commitment C here. Okay, if this is the case, he'll output C1 and C2. So it's easy to see that this protocol satisfies completeness because honest prover will output correct opening F1, F2 for C1 and C2. And it's also easy to see that it also have knowledge soundness, because as long as some malicious prover outputting some F1, F2 that is with very small norm and is the correct opening of C1, C2, then we can extract something like F1 plus B times F2, which is the correct opening of the commitment C1 plus B times C2, right? And also because verify already checked that this equals C, we obtain some valid opening for the input commitment C that has a norm that's smaller than capital B. So this is indeed a reduction of knowledge. So that's this. And then that's about decomposition. And after that, the folding part, and the other part is the folding scheme, which is I think is more interesting part. To do this, let's consider a simple example where we just want to fold two vectors into one, okay? And now we are in a slightly better situation because these input opening are having norm that's much smaller than before. They have a norm that's smaller than small b here. And now the idea to rescue this naive idea is to set R to be some very, very small random scalar. And hopefully, because initially they are very, very small, and also R is very, very small, then after folding, this commitment opening can still be as small as capital B, even though it's larger than small b, but still smaller than capital B. So the good thing here is that now completeness holds, because we can always guarantee after folding is still in this relation R type B. However, there are some issues in terms of knowledge extraction. The main issue is that to see what's the issue, let me illustrate by see how we typically extract a witness, okay? So let's even consider a simpler problem. Let's for simplicity assume that malicious prover is a perfect malicious prover that always gives you some correct output witness for the folded commitments. And in that case, we can feed it into two different random scalar and he'll output two different valid openings for these commitments, okay? Namely WFDX and WFDY for the folding commitment and CFDX and CFDY. And our idea is the following. So given this, we can build a system of linear equations where we set this W1 and W2 to be some variables using coefficient Rx, L1, Ry, and the value WFDX and WFDY. And then we can solve these linear equations to obtain some witness W1 and W2 that satisfy these linear equations. And then by the linear homomorphic property of matrix multiplication, we can actually easily argue that C1 equals AW1 and C2 equals AW2. And that is with no problem. But the key issue here is that the solution we find may not have small norms. It's totally possible that this norm of this extracted witness can be very, really large. It's much larger than this small base B. The reason is that in this first term, even the first term, the WFDX, WFDY can be as large as capital B. So their difference might be as large as 2B. And even worse, the right-hand side, this term is some inverse of some differences. And we have no control of the norm of the inverse of these elements. So in general, to recap, this naive solution doesn't work. The main reason is that it's very hard for us to extract some witness that's valid, but also have a very, very small norm, namely even smaller than this capital B. And this seems inherently hard, right, without doing anything else, because what we start with is already some witness that can be as large, have norm as large as capital B. So now the key question is, how can we address this limitation? And the idea is to add some extra procedures here. For example, to let the prover to additionally prove, okay, I indeed know some witness F1, F2 that is very, very small. And moreover, this small vector F1, F2 is indeed the commitment to the C1 and C2 that satisfy this matrix relation. And one naive way to do this is just to directly ask the prover to send this witness F1, F2 in the clear to the verifier as a folding proof, okay? And the verifier will just check F1, F2 are indeed with small norms, and they are indeed the matrix multiplication with respect to C1 and C2. And this works well for obtaining an extractor, but it's not very well in terms of efficiency, because now the folding verifier has linear time complexity, because the F1, F2 has linear length, right? The length is linear to the number of witness elements. And as we mentioned before, we really need some verifier that has sublinear complexity in order to obtain a piecemeal SNARK. And moreover, this complexity of verifier is very, very related to the recursive verifier circuit sizes. So now the question is that this naive protocol doesn't work. How can we efficiently instantiate this range check or norm constraint protocol? So to do that, our idea is to use the sum check. To recap, our main problem is the following. Say we have some commitment, short commitment, that commit to some oracle vectors, F, and the prover wants to show that he knows this vector, and for every entry of this vector is this very, very small norm. And now for simplicity, let's just assume that every entry is just an integer rather than a polynomial with integer coefficients. But the idea is similar, okay? And now the problem is to check that for every entry of this vector, which is an integer, every entry is in the range between -b and b here, okay? And our first step is to transform this norm constraint check to some algebraic check, meaning that we want to prove that for each entry, this HFI equals 0. And HFI is defined as following. It's defined as a product of many terms related to Fi. Okay, and you can see if this entry Fi is indeed in this range between -b and b, then exactly one term here will be 0. So the product will be 0. And if it is not in this range, then none of the term will be 0. So the product will also not be 0. So that means these two problem is equivalent. And this transformation has no problem. And now every arithmetic is over the integer, but we can, for efficiency, we can map them to some prime fields with respect to some prime modulus Q here. This argument will still hold as long as the prime modulus Q is large enough, namely larger than 2b is already enough. And after that, we can do some syntactical change to change this vector algebraic check to some polynomial check. So we can embed these elements HFI to the Boolean hypercube of some multivariate polynomial. by multivariate polynomial, I mean it's a polynomial with many formal variables, like x1 times x2 is the two variable polynomials. And now, after embedding this value into Boolean hypercube, the problem becomes to check that for some oracle polynomial, which is committed in some commitments, this oracle polynomial satisfies the evaluation of the Boolean hypercube are 0 everywhere. And this is so-called polynomial zero-check problem. And with some tricks used by some previous work like Hyperplonk and Spartan, we can transform them into a very famous problem called polynomial sum-check problem. And the goal is to prove that for this oracle polynomial, the sum of the evaluation on some Boolean Boolean hypercube equals some claim value S, public claim value S. So to recap, what we have done is that we transformed the original norm constraint check problem into a new problem that is famously known, which is the sum check problem. And the nice thing here is that we do have very famous and classical protocol called sum check protocol dating back to Land, Fortnow, and Karlov and Nissan in 1992. And subsequently, there are many works to improve the concrete efficiency of it. So the proof time is actually very, very efficient, linear to n. And the verified complexity is logarithmic to n, where n is the vector length, and also proportional to b. But b is something we can set because the small base b is something we can set ourselves. Usually, we can just set it to be less than 4 or less than 2. So this is actually very, very efficient. And in some sense, this sum check protocol is some reduction from this sum check claim to this evaluation claim. Basically, finally, you still need to check some evaluation statements with respect to some Martinian polynomial at some random point. That if this holds true, then with high probability, with overwhelming probability, the sum check claim will also hold true. So the final question is, who will be responsible for checking this, right? One option is to directly ask this rank check verifier or folding verifier to check this. But unfortunately, that's too expensive because a single Martinian evaluation already takes you O(n) time complexity. So it's not affordable for folding verifier if you want to achieve very efficient folding verifier complexity. But fortunately, the key observation here is that this evaluation statement itself is actually pretty easy to fold. If you understand this evaluation statements as a relation, what these evaluation points are, and this claim evaluation value t to be the commitments or the instance of this relation, and the witness to be this polynomial, then it's actually very easy to fold. For example, consider a simple case where you have two evaluation statements with the same evaluation points. Then you only need to fold and do a random combination on the evaluation value t here, and delay the evaluation check till the very end. And suppose you have two evaluation statements that have different evaluation points, which is slightly more complicated, but you can trust me that you can run another sum check to reduce it to a single evaluation check instead. So you can merge two evaluation check to one evaluation check. And no matter what is the case, you can always preserve this complexity, folding complexity, to be logarithmic to n. So this leads to our final solution, where our idea is to expand this commitment opening relation a little bit to also include these evaluation statements inside, which is also easy to fold. And in each step, you just fold this evaluation statement and commit opening relation, but delay the evaluation check till the very end. And in these cases, the folding verifier can still preserve this very, very efficient complexity, which is logarithmic to n. Okay, so that's the high-level idea. In order to make it work, however, and work it very nicely, there are many subtleties to solve. The first thing is that previously I'm cheating a little bit. I'm saying that every element is just an integer, but for efficiency reason and for some security reason, we do have to work over some ring RQ here. And that means we can no longer run a sum check over a prime field. We have to run a sum check over a vector space of prime field or equivalently some ring. But fortunately, as observed by some previous work, we can run sum check over rings easily with some slight modification without loss of many efficiency. However, if you run naively for this protocol, in order to make it work, you really have to use a very, very large prime modulus Q, which can be as large as 250-60-bit prime modulus. The main reason is that in this sum check over rings, the verifier has to sample some challenge in each round, which is inside some subset of RQ. And this subset has to be really, really large and also needs to satisfy certain invertible property, which holds for free in prime field but not over ring. So therefore, in order to satisfy this requirement, the easiest thing we can do is to set this Q to be really, really large. If you set Q to be really, really large, you can easily achieve this property. However, in practice, we want some very small prime modulus Q, like 64 bits prime modulus or 32-bit prime modulus Q. And in that case, the reason we want this is that we can represent every ZQ elements in a single word in CPU or GPU and avoid big number arithmetics, which is quite expensive. But fortunately, with some optimization, we can achieve this and use some prime modulus Q can be as small as 32 bits or 64-bit primes. But I want to note here that you really cannot use very, very small Q like binary, like 2 or 3 or something, because as I said before, in order to make the Module SIS assumption hold, you still have to choose some Q to be relatively large, and the norm bound will be even smaller than this Q, significantly smaller. So that's it. However, as mentioned before, this is just a toy example. But in order to obtain a piecemeal SNARK, we really need to fold some relation that's more complicated. So beyond proving this commitment opening relation, we also have to prove this like other statements, which is local computation chunks is correct and the folding verifier is correctly verified. And therefore, that means in this relation, we also represent and express these kind of computation statements beyond the commitment opening relation. So that requires us to augment this relation to also support some NP-complete language to represent this computation. And our solution is to support this so-called customized constraint system relation introduced by Srinath, Justin Taylor, and Real Wabi in 2023. So in general, this is just a generalization of the traditional R1CS constraint system that allows you to use high-degree gates. And the nice thing about it is it allows you to express arbitrary NP computation efficiently in some relations or in some circuits. And after that, we'll also obtain a folding scheme for that, which is not much harder than the commitment opening relation folding. And the key highlight here is that we can reuse this decomposition plus folding framework here. And I think that's a really useful framework. Okay, so finally, let me focus on give you a little bit information on how efficient it can be. I think this is one of the most important slides I want to say about in this talk, is that first, you can see that in this lattice folding scheme, we have replaced those Patterson commitments with these ATA commitments. That means we have removed those group exponentiations with some ring operations over RQ. And as I mentioned before, with a correct implementation and optimizations, these ATA commitments can actually be really, really fast, even in CPU, can approach some performance of some hash functions. And even better, we see that there are tons of optimizations and very, very fancy implementations of FHE in this FHE industry. And the good thing is that they are exactly doing the same operations here, right? Is some like NTT or very fast operation over some RQ. So that means we can reuse all of these hardware optimizations or implementation from FHE and make them very, very efficient for LatticeFold as well. So I think this is really promising, and in some sense, in the future, I think it can be blazingly fast. And the second, in terms of this recursive folding verifier circuit, our circuit is dominated by the sum check verifier, which involves logarithmic number of hashes and ring operations. But the key highlight here is that compared to those pre-quantum schemes, we don't need any cycle for rings or which is in their case they need cycle curves, and all operations in this recursive circuits is over the same ring RQ. So every operation can be natively represented in arithmetic circuits instead of being simulated in a different field, which is the case for those pre-quantum schemes. And that is also one of the main reasons that we can actually obtain very competitive recursive circuit sizes. And finally, let me have one word about this piecemeal SNARK proof sizes. So when you do this piecemeal SNARK compilation naively, finally you obtain a final folding instance and witness pairs. And the folding instance can actually be really, really small. But the issue is about this folding witness. say you have some arithmetic circuits over 2 to 30 gates you want to prove, which is really, really large. And in practice, usually you don't want to split into too many chunks, right? Because every chunk is still incurs some extra overheads because you have to generate these folding verified circuits. So it's more reasonable to consider to split into a reasonably large number of chunks. For example, 10,000 or like definitely less than 100,000. And in that case, each chunk statement, even though much smaller than before, can still have a large witness, can have like tens of megabytes witness size, which is still pretty large. But the nice thing here about here is that you can easily compress one thing further and make the proof much smaller. The idea is to finally use a single post-quantum secure monolithic SNARK to further compress this folding instance with pair checking statements and delegate this checking to the prover and let the prover to generate stock proof for this. And the nice thing about this is that with the recent advance, this stock proof can be as small as less than 100 kilobytes. And moreover, it should be very, very easy to verify this proof. And in general, after combining this piecemeal SNARK with this final compression method, we can obtain a very, very efficient SNARK proof that has very efficient prover, very small proof sizes, and very fast verifier, and it's post-quantum secure. So that's the like the high-level idea of how efficient it could be. And that's basically it. And in summary, we introduced the first lattice-based folding scheme based on the RTI commitments, which gives you a memory efficient and post-quantum secure SNARK that has fast provers. And along the way, also introduced many generic techniques for folding lattice-based commitments. That means it not only works for RTI, it works for almost all kinds of lattice-based commitments. And one last thing is here that I want to mention a concurrent work. I think also someone has mentioned this. So recently there's a new work that is authored by Benedict, Precious, Wilson, and William. They have built a new folding scheme that purely from hashing, which is really great. There's even no need for lattice crypto. Even though I mentioned this lattice crypto is almost symmetrical lattice crypto because add hash function is also very fast. But if without it, it can be even faster, which is nice. And they also mentioned some general optimization techniques for this piecemeal SNARK compilation that actually can also work for LatticeFold and further improve the efficiency of LatticeFold. And compared to our work, the trade-off of their work is that first they have a larger recursive verified circuits because they need to perform many hash operations, significantly more hash operation in the recursive circuits. So that's why they have a much larger recursive verified circuits. And on the other hand, they only support bounded, like constant number of folding steps. And compared to our that we can support unbounded number of folding steps. And in particular, they also mentioned there exists a concrete attack in their cases if you fold for more than a constant number of folding steps. So that's the trade-off between these two schemes. And finally, let me also mention some we believe that can also be able to fold in this table lookup relation, which is a relation that's proved some witness inside some preset tables. And recently, there's an elegant work called Lasso that's built a lookup arguments from some check. And we believe that can be easily integrated into our setting because okay, it's very like some check friendly, very smart some check friendly. And I think the second is that I think highlight here is we really hope that can be some very, very efficient and very, very optimized industry level implementation for LatticeFold. And I'm really excited to see how it performs, and hopefully that can possibly be a game changer for proving really, really large statements by combining all sorts of techniques and also combining those really elegant stock proof together. Yeah, that's basically it. And now I'm happy to answer more questions. I think in the chat there might be some questions I haven't looked at yet. Now maybe I can answer them. Yeah, thank you so much.
Thanks a lot, Binyi. There was a question that I missed when you were talking about the decomposition. So to be able to change from relations on capital B to small b. You were talking about scalars between. Yeah, there was a question whether the decomposition had to be unique or not, because what you should.
decomposition has to be unique or not. Oh, I see. So
I
decomposition.
mean, because of negative numbers, it might be not unique as at least as you stated that.
So you are saying basically an integer, right? An integer, whether
Yeah,
the
I mean, there is
decomposition-
base B decomposition is not unique for numbers bounded from minus b to the power k to b to the power k. There are multiple decompositions.
That is actually unique because every it's not 0 to the b, it's minus small b to small b, right? For example, if you have 7, it will be correspond to 1, 1, 1, correct, right? 7 is 1, 1, 1.
Yes, but it will also.
And if it's minus 7, then it's minus 1, minus 1, minus 1.
No, please hear me out. B minus 1 is both b minus 1 and minus 1 plus b, okay? It's
sorry?
not unique. My point is that it is not unique. Base B decomposition of b minus 1 can be both.
Not base B minus 1.
I'll write it in chat. I'll write it in chat to be precise.
No, not b minus 1 over b. So that's base is 1 b squared, b third, so on and so forth, right?
Yeah,
and
please.
Suppose b is 2, okay? B, for example, if suppose b is 2, then for every integer that's less than, say, less than 8, right? And let's say small b to be 2, right? And 7 has this unique representation to be 1 times 1 plus 1 times 2 plus 1 times 4, correct?
No.
Why not?
Incorrect. This is another representation of 7. Please take a look.
Oh, I see your point. I mean, the decomposition algorithm itself is unique. You understand? So
yeah, I'm saying that the composition is not unique.
I see. Oh, I see you. Oh, I think you are.
Maybe it's not a problem for you.
I see your point. I see your point. You are not talking about this algorithm is deterministic. You are saying that they have different decompositions. I see. So let me. That's a good question, and it's not a problem in our case indeed. So let me see if I can reshare my slides. Okay. Yeah. Did I stop sharing? Okay, let me share. Okay, here. Yeah. So yeah, that's actually a pretty good question. So I kind of misunderstood your meaning. So I saw you mean that this algorithm is non-deterministic. This algorithm is deterministic, but you are right. For a single value, they might have different decompositions, right? But what we need is just we only need some valid opening. By what valid opening, it means that it satisfies matrix multiplication relation and have some small norms. That's enough. And the uniqueness is not information theoretic. It's just by some computational assumption by Module SIS. So as you see here, like first completeness holds. I think what you are concerned about is about the North soundness, right? And here, this North soundness, when you extract, you can see here, when you extract is F1 plus BF2, even though it's not the only decomposition for C1 plus BC2, definitely it's not, because information theoretically it cannot be possible to be unique. But it still satisfies matrix relation, right? Satisfies the matrix multiplication relation, and it's also having small norm. And this binding property now is computational, not information theoretic, because we are relying on some lattice assumption there to argue this binding property. And still, we can see here, the relation statement itself is just saying that it's in the relation as long as C is a matrix multiplication of A F star, and F star is having small norm. That's the only requirement we need, right? So it's still a correct, valid witness for the input relation. Yeah, so that's it. But it's a really good question. And sorry I misunderstood initially, but now I think you now are clear about this. Okay. Yeah, thank you so much.
Yeah, I'm also, do I understand correctly that if we are, I actually have a lot of questions, to be honest. Maybe I could just ask them after if it's, maybe somebody else wants to ask something, because I could, I think, easily consume all remaining time on my questions. So maybe anybody else?
If you don't mind, I would also like to ask a couple of questions. So here, thanks a lot for your talk. Here you've been talking about using hashtag commitments, but I'm aware that there are other commitments. I think there is a paper for 2018 on lattice-based zero-knowledge proofs that have been using combinations of hashtag and BDLOP commitments.
I see, yeah.
So I was wondering if you also looked at other commitments, or because hashtag commitments are quite old.
Yes, yes, that's a good question, very good question. So the reason we choose RTI first is because of its efficiency. I think it's actually very, very efficient. And compared to these BDLP commitments, one of the key advantages of RTI is that it's very, very compact. It's like no matter how large the witness it is, the commitment itself is always a constant. But I think the BDLP commitment, I think has some linear complexity, like at least is not independent with message vector length. And it can be long, relatively long compared to the message size. So that's one of the reasons we choose RTI. And in RTI, the trade-off is that the witness should have some small normal constraints, but it turns out it's actually pretty, it's not that hard to deal with in the folding scenario. So that's the main reason we choose RTI. Yeah.
You know, in this paper, they talk about the same problem, and that's why I think they combined the two commitment schemes to try to be able to work on larger modulo thanks to the BDLAP scheme, but still maintain smaller size. I'm not very
I see.
the paper and lattice in general, so I may be wrong, but
that's interesting.
Wondering.
Yeah, and I want to add one more thing here. You are right. The advantage of BDLP is that it supports larger message size space. But the really nice thing about here is that in a folding scenario, we actually don't need such a property. I didn't mention this, but basically in this final folding scheme for this CCS relation, the witness in CCS relation is actually can have arbitrary large norms. It's arbitrary ring elements. But the nice thing here is that we can still commit the RTI using the small norm messages, which is some decomposition of this large witness. And the only thing we will need to further prove is that there exists some matrix multiplication relation with respect to some gadget matrix between this CCS relation and this small norm messages. And as long as small norm message is fixed, then this CCS relation is also fixed. And this the binding of this small norm messages is achieved using this binding property of Module SIS or anti-commitments. So in our case, we actually don't need to have that stronger property for commitment schemes.
Yeah. Thanks a lot.
Yeah, so I think I have formulated the question that I want to ask. So considering anti-commitments, when we are looking on Pedersen-based commitments, one of the very desirable properties of the folding schemes is that because you are not actually doing SNARKs, you can use the fact that small values are easier to commit to. So, like, it's faster to commit to small values than to large ones.
I see.
And as far as I understand, ITI commitments do not have this property, right?
Other commitments is kind of hard to say because, like, you already have the constraints that the message itself should be small, right?
No. I mean, to be precise, I have some trouble with. So basically, when you have a large statement, you so I mean, if you have large coefficients, you represent it as a lot of small, like base B small individual commitments, and so you are paying for each of them the full commitment cost, right? So if, for example, your base B should be like really small, for some check to be efficient. Like it should be base 3 or base 5, something like quite small.
Actually, you have to remember there are two B here, right?
Yes, B small. I'm talking about B small. For
B
each
small,
B small.
Yeah, the small b has nothing to do with ATA commitments, right? The other
no,
commitments...
it has. Can you open the slide? Can you open the slide about like the previous one?
I think I know what you mean here is that
I mean that your folding procedure requires you to communicate this.
I see your point.
Pieces. It is pieces.
So
and committing to each piece might be hard. Like I mean, there are a lot of pieces that you need to communicate.
I see your point. So like you are saying that in this decompose protocol, you're exactly talking about this decompose protocol, the prover needs to compute this C1 and C2 here. And in this case, F1, F2 are actually small norm, right? And you are saying that you have to commit many of these. And in Patterson cases, if F1, F2 is really, really small, then actually it can be much more efficient than commit to some large scalars, I think. And you are questioning why can we have a similar optimizations for here in lattice cases, right? And that's a very good question. I haven't thought about this deeply. So I guess your question is like, suppose we have a really like binary vector, for example, binary vector of F. Can we compute? Yeah, and can we compute ATA even more efficiently, right? I think that might be possible because that's basically just some, like if it's binary, then it's just some combination, a sum of some columns of these A matrices, right? And this is this can be much faster than just computing some R-cube multiplications. So we might be able to have some similar optimizations in the ATA cases.
Yeah, I mean, I am just trying to understand. So what is compared to what? So for example, if we are not doing this optimization, so my question was like, do you know if this optimization exists? Because if it would exist, then like if it doesn't exist, then we are not comparing the cost of one commitment on the side of like Pedersen world to the to one commitment in the Ashtai world, but we are comparing like logarithmic amount of this like log of magnitude of these commitments to a single commitment in a Pedersen world.
I see your point. Very good question. So you are saying in the Pedersen cases, because we don't have this splitting process, we only need to compute a single commitment for a long vector. And in our cases, we're actually committing to the beyond these commitments. We also need in the decomposition scenario, we also need to commit something else, right? Which adds some extra overhead. And if you don't have this optimization, you are saying that we're actually comparing to committing logarithmic or like at least like k commitments versus committing one commitments, right? That's a very good question. I think we should be able to have some optimizations for very small scalars. But
I would also expect it should exist. I would also expect you are doing something linear after all.
Linear of what?
I mean, the operations that you are doing are already multiplications which use bit decomposition. You could like do the bit decomposition of the right-hand side.
Actually, let me rephrase a little bit. Actually, I'm thinking actually don't need to do many commitments, actually, to be honest. The reason is that I think you can directly decompose using C. You don't need to recompute these commitments. This is just for illustration purpose. And there has some simpler, I think so, right?
No, you can't. You need to decompose your original vector. But multiplying by small numbers is faster than using constant. Like I mean, it still should be faster than like this naive expectation.
Yes.
Yeah, I've just looked into similar. Like when I've read your paper, I actually walked back to Pedersen world and did some like research on like using this to improve range checks in Pedersen world, and actually it looks even better there.
I see. You're saying that you use this trick for a range check trick for Pedersen. and obtain a similar scheme for Patterson, I guess, right? You're saying.
So actually, I still wonder if you could, like for LatticeFold, if you could do multiple foldings without doing this split and merge thing. Like if you could do multiple foldings without your norm bound overflowing. If you could do this, it would be like great. But
I see.
there are some subtleties there. But in Patterson world, it is doable. Like, but
yeah,
I'm
of course,
not sure.
Because
I'm not sure.
In Patterson, there's no normal constraints unless you want to have some optimizations in terms of scalar size, right?
There is norm constraint in the sense that
I mean, in terms of security,
you want your limbs to not overflow. You still want your limbs to not overflow, so you cannot do it infinitely.
I see.
But because my purpose was actually doing non-native arithmetics in Patterson.
I see.
Probably it is also applicable to this.
I see.
And
yeah,
actually,
that's a very good point.
It's also interesting.
So I want to add one more thing here is that first, even you do Patterson, you have these tricks. You still, again, it's still discrete log assumption. It's definitely not post-quantum secure, right? If you consider post-quantum security, definitely you should do R-type, I think. Of course. Yeah. And yeah. Right. And yes, I think you mentioned a really good question, whether we can remove this splitting procedure. But I think if you want to do infinite number of folding in the lattice world, this seems quite hard. But maybe there's a way to do that.
Maybe 2 to the power 40 foldings is enough. Maybe you don't need. Maybe you don't need infinite. Maybe 2 to the power 40 is enough. And also actually quite interesting thing that SNARKs are also, I mean, FRI based or like erasure code based stuff is also evolving to the question how to compress low magnitude low modulus values into higher in more efficiently. Like for example, there is a recent work on which uses extension of F2. And as a base layer, it uses breakdown. And I think that breakdown is directly analogous to the recent work on folding without homomorphism by Bunset and others. So breakdown is like square root of n style construction, analogous to the folding construction that Bunset et al. Recently suggested. So this F2 extension technique can be also used in it. So like actually a lot of folding schemes are like converging to the idea that you should use small base decomposition. And now somehow ensure that your proof system handles it like fast enough, like that your commitment scheme allows you to commit faster to the small values.
So what I see. So what's the general question here? You want to compare?
No, it's not. Okay, I have no more questions. Or maybe
I see. It's a comment. I see. Then agree. Yeah. So I guess I think one interesting question here is that whether we can support this kind of extension of binary fields in the lattice world, which I think is pretty hard, because usually because if you suppose that you are using this Module SIS assumption, you really need this prime modulus Q to be usually relatively large, like usually at least 32 bits. Like that means that you might be able to use Mersenne prime fields, but I don't see how it can be easily used these binary fields. It seems quite hard in the lattice world setting, but I think even using Mersenne prime fields can be quite fast in the lattice world as well. Yeah. Yeah, thank you for the question and comments. Yeah, that's quite helpful.
I have one addition, by the way. If you somehow ensure that your circuit has small values, then there is actually quite an easy construction which allows you to compute your intermediate commit. Okay, maybe not. No, never mind. No. But there are definitely optimizations for small values.
I see. Yeah, I agree. I believe that. For example, I think in Lasso they also mentioned a lot of optimization with respect to small scalars. Yeah. Okay. Any other questions?
Thank
you. No, I don't see any other questions. I had one, but it's very general. But I'm not sure if we have time. So I will just send it to you offline, if you don't mind.
Yeah, sounds good.
Thanks a lot, Binyi, for coming today and for this presentation. It was very interesting. And we've had you 3 times, so I'm sure we're going to have you another time soon.
Thank you
again, and thanks a lot everyone for joining us.
Yeah, thank you so much for the invite, and yeah, it's a happy experience. Yeah, thank you.